Welcome to IMSC, another edition of Science Day. From the schools, our student friends, teachers, from the colleges, wherever you might have come from. So this tradition has been going on for a few years here, and essentially the day's program is going to be a few talks in the morning. Then you get to meet some of our scientists. You get to talk, you get to ask them whatever question you want. There are of course the demos in the afternoon, don't miss that. The quiz, prelims are going to happen around 12:15, I believe. Yeah, that's at the same time as the scientist meeting, the Grill the Scientist part. And the quiz main is going to happen around 4:30. So we'll begin in a few minutes. So you can go back to your standard talk state. But whoever has mobile phones, before the talk starts, please silence them or switch them off. And once again, in 10 minutes, we shall begin this year's edition of IMSC Open Day. The minute, so the talks will be streamed live at some of our lecture halls, classrooms. So they are the Alladi Ramakrishnan Hall, room 326 and room 327. So if perhaps you don't find seats here later, you can always take the corridor from here and then take the stairs up. So the top floor and the floor just below that. So I think we are ready. I'm going to hand the mic over to our director, Professor R. Balasubramaniam, and he will welcome you all to this edition of IMSC's Open Day.
Dear students, it's nice to see a lot of young faces. And how many of you do understand English, and how many would be comfortable if the proceedings are in Tamil? Can you raise your hands? How many will be comfortable with English? All are comfortable with English? Sure, no problems. Okay. Oh, okay. That is nice. That also helps us a lot, in the sense that some of the organizers and some of the lecturers may not be comfortable with the Tamil, and therefore if the proceedings can be done in English, that will be much better. But at least some of them, a few of them may be able to talk in Tamil, I think. Yeah. Sorry? None of speakers will be able to talk in Tamil. Okay. Okay, see, this Open Day is an idea which practically all the institutions follow, of a day when you get the school children from the various schools nearby to know what this institute is doing. Now, once you want to decide your future, you should know what the various institutes are doing. I mean, what type of work they are doing, and either in industry or in academics and so on and so forth. And normally that is done on February 28, which happens to be this, it happens to be what? Science Day. Yes. But you know, since practically every organization seems to be having it only on February 28, and we thought that we should have on a different day so that the students would be able to attend this, and then also would be able to attend any other programs. And I would probably think that for most of the students, this might be their first visit to this institute. And probably for most of them, you will not have even heard this about this institute before you received a formal invitation to come and attend this Open Day. Therefore, I should probably say something about this institute, what this institute is doing. This institute essentially concentrates on research in mathematics, physics and computer science. And the research in physics as well as in computer science are of more of a theoretical nature. We do not have a laboratory facility. Even though when you see the various programs that my colleagues have organized, you won't believe that we don't have an expertise in the experiments, but the thing is that we don't have really the laboratories here, and we have only the theory in physics. And I should even say that our computer science is also only theory. And therefore, make it very specific. We call our research as theoretical physics as well as a theoretical computer science. And I don't think there is no reason to call theoretical mathematics, because I mean anyway in mathematics there is nothing other than theory. That's what we do. This institute started as a state government institute in 1962, as most of you might have seen in the plaques which are in the front of these buildings. But the major finance now comes from the Department of Atomic Energy. And one thing I should say about that is that this institute has a very good library, and some of you who are interested in knowing more should be able to attend this in library here and even talk to the staff members here, not necessarily only today, at any other time. And the institute is also doing various outreach programs, okay, like this one, and otherwise most of our colleagues go to the various colleges and gives lectures, and we have the interaction with the universities. And at least as far as mathematics is concerned, this institute also serves as the venue for the various Olympiad programs which are conducted in mathematics. I assume that all of you would have known something about the Olympiad programs. And these Olympiad programs, at least in this part of this is the Olympiads program, at least in this part of this, is conducted by an organization called the AMTI. And those Olympiad programs also, this happens to be the venue. And therefore, those of you who might be very interested in knowing more of academics, more towards research, even though you may not be a research mathematician or a research physics, but somebody who knows more, and therefore even if you decide to go for an industry or other work, that you want to know more so that you would be able to utilize your expertise in the various industrial or modeling works that you want to do, this will be a nice place which you should visit more frequently and try to interact with our colleagues and try to learn more. And therefore, let this be the start. Let it be the first day for you to come here, and I hope that your association with this institute would continue, and you would always be keeping touch with us, and so that we would try to see whatever best we can do for an academic atmosphere in this part of this country. And thank you.
That was our director, Sir Balasubramaniam. So after that, I'm not going to waste any more time. We're going to go directly to our first talk by Professor Denis Benoit. He's from the University of Bordeaux in France, and he's going to be speaking on Diophantine equations.
I would like to explain what Diophantine equations are. So I start with some words about Diophantus. So Diophantus was a Greek mathematician who lived in the 3rd century.
This one?
So it was a long time ago. He lived in Alexandria, and he interested in solutions of equations. And it was quite special for his time because usually Greek mathematicians interested in geometry, but Diophantus interested in equations. So in the 3rd century, mathematicians knew normally integers and rational numbers. So Diophantus was interested in solutions of equations, but he considered only rational solutions or integral solutions. And in 17th century, French mathematician Pierre Fermat started, in some sense, the modern theory of equations, algebraic equations with integral solutions. So I will give just an example to explain the subject. So consider a very, very simple equation, something like so it's easy to resolve it. Yeah? So x is equal to 3 by 5. But if we consider this equation as a Diophantine equation, so as an equation, if we search only integral solutions, so this solution is not integral. So as Diophantine equation, this equation has no solutions. So has no solutions. In the set of all integers. Yeah. Okay, let's now look another example. So something like this. So this equation is more complicated, but again, let's look only for solutions which are integers. Okay. So we see that we don't need to have an explicit formula for x to find integers x satisfying this equation. So for example, we can do the following thing. We write this equation in the form and we see that x should divide 2. So we can list all divisors of 2. So test all divisors. So we test the following numbers: 1, 2, -1, and -2. And if you test each number, you'll see that only one works. Only one of these 4 integers is the solution of this equation. This is 2. So the solution, the unique solution of this equation in integers is 2. So we can now think that find the integral solutions is more easy than find all solutions. Now let's look the third example. Something like this. So we look for all x, y, and z, which should be integers, such that this equality holds. So the goal is find all x, y, and z which should be integers, such that this equality holds. So we can certainly do the following thing. Yeah, so we can choose 2 integers and write the third as a function of chosen integers. For example, we have the following. Okay, so let's take y and z. The problem is we don't know if x will be integer or not. So this formula is absolutely unuseful if you look for solutions which are integers, because we cannot say if the third number is an integer or not. So we should proceed by a different way. Let's look again this equation. Can we find at least one solution in integers? Sure, we can take all variables equal to 0. So if x is equal to y is equal to z is equal to 0, so this gives the solution. Okay. Can we find other solutions? It seems to be difficult. In fact, we will prove that there is no other solutions. So how can we prove it? So let's write this equation in the following form. That's okay? And so we see that 2 divides x cubed. But if x cubed is an integer, so x should be even. So we can write x as 2 multiplied by another integer, say x1. Okay, so replace x by 2x1 here. So what we obtain? We obtain 8x1 cubed plus 2y cubed plus 4z cubed is equal to 0. So we can divide all by 2. Okay, we divide. We obtain 4x1 cubed plus y cubed plus 2z cubed is equal to 0. So we obtain something similar. But here we have x1 instead z. So we can repeat the same procedure. Here we saw that x should be even. Here we see that y should be even. So we replace y by 2y1 and we obtain so we can divide again. Again, we obtain the same equation, just the variables have changed. So, again, we repeat the same argument, and we see that z should be even. So z should write as 2z1, where z1 is an integer. Okay. We replace z by 2z1. And we obtain this equation. Now we can again divide by 2. We obtain the same equation as in the beginning. But x, y, and z are replaced by x1, y1, and z1. So what we obtained finally? So if x, y, and z is a solution then x, y, and z are all even. And x1, y1, z1 is again a solution of the same equation. So we can divide x, y, and z by 2, and this gives a new solution. So we can repeat the same thing several times. We have a new solution. So we apply the same procedure. We obtain again a solution, but which is obtained dividing the initial solution by 2. And it seems that we can repeat this procedure infinitely many times. Is it possible? In principle, not, because if x is an integer which is not 0, we cannot divide x infinitely many times by 2. So this shows that the unique possibility is that all variables are equal to 0. So this proves that this equation has only one solution, which we found in the beginning. X, Y, and Z are all zeros. So this is somehow non-trivial example of a Diophantine equation. And you see that the solution is quite particular. We use properties of divisibility of integers and not formulas. Let's look the following. can we find all solutions of this equation in integers? So this example is in some sense different. Again, it is not too much practical to use formulas. For example, if you write x squared equal to y squared plus 1, and if we write x as a square root, so we don't know if this root is an integer or not. So this formula is not too much useful. But we can proceed by another way. We can decompose the left-hand side. So we have the product of two integers, which is equal to 1. What we can say about these integers? So one should be, or both are equal to 1, or both are equal to minus 1. So let's look so if the both factors are 1, when if we add the first to the second, we obtain that 2x is 2, x is 1, and therefore y is 0. If they both are equal to minus 1, again, we take the sum of both. We obtain that 2x is minus 2. Therefore, x is minus 1. And y is 0. So we found two solutions. The first one is x is equal to 1, y is 0. And the second, x is minus 1 and y is 0. And there is no other solutions. So here is an exercise for you. Find all integers x and y such that x cube minus y cube is equal to 91. Okay, so now I would like to say something about the theory of differential equations. So in the first example, we saw that if there is only one variable, it is really easy to resolve a Diophantine equation. So we will consider only Diophantine equations in several variables. And the simplest equations are so-called linear equations. So here is an example of such an equation. So again, we want to find all integers x and y such that this sum is equal to 1. So again, we see that it is not useful to write one variable as a function of another one. For example, we can write y as 1 minus 121x divided by 52. But we need to find the integral solutions, and we don't know if this thing is divisible by 52 or not. So again, one should proceed by another way. So we can proceed using so-called Euclidean division. So we have two coefficients, and they can divide, for example, the first by the second. What we obtain? So I can write 121 as 52 times 2. But I should add something. What should I add? I think 17. Okay, now I divide 52 by 17. So I can multiply 17 by 3. This gives 51, and I should add 1. Okay, now let's look these formulas as follows. I start with 1. I write 1 as 52 minus 17 times 3. And now I replace 17 here by 121 minus 52 by 2 times 3 I have here 121 3 times and minus here. And I have 52 here and 52 here times 2 times 3. So totally I have 52 times 7. You can check that this works. But here we obtain a solution of this equation. We can take x equal to minus 3 and y equal to 7. So we find at least one solution of this equation. Okay. So what we can find in general. So if we have 3 integers a, b, c given, we can look for the following question. And we want to find all integers satisfying this equation. So we can look for a common greatest divisor of a and b. Greatest common divisor. And so it's easy to see that if the greatest common divisor of a and b does not divide C, when there is no solutions. If not, elsewhere, this procedure, such a procedure gives always a method to find the solution. Elsewhere we can find the solutions using Euclidean division. So this is because this equation is very simple. More complicated equations are the following form. They are so-called Pell equations. So those are Diophantine equations of the following form. Where A is a given integer. For example, can consider something like this. And this equation has a solution. We can, for example, x equal to 3 and y is equal to 2. In fact, one can prove that there exist infinitely many solutions. So Pell's equations were studied maybe approximately 300 years ago. Let me now say something about the problems which were studied very recently. So we will consider, for example, the following Diophantine equations. So we will look for the equations, for example, like this one. I can in fact write more or less arbitrary thing here, which should be a polynomial, something like this. And we can define the degree of a polynomial which is the highest of degrees which appear here. So for example, here the degree is 4, here 5, here 7, here 1, here 1, here 0. So the degree of f here is 7. So the following theorem was proved by the German mathematician Siegel at 29. So assume that f cannot be decomposed in product of tupled over polynomials. Then this equation has only finitely many solutions in integers. If the degree of f is at least 3, and the following thing was proved by another German mathematician, Faltings, at 83, which says that if the degree of f is bigger or equal to 4, then this equation has only finitely many solutions. Even in rational numbers. So you see that this is a long story which started 4,000 years ago, and such wonderful things were proved only in the 20th century. So I stop here.
That is Professor Denis Benoit speaking about Diophant-10 equations.